Welcome to this introduction video of Windows RF Calculator, or abbreviated WinRFCalc. I want to show you in this video the capabilities of the software program by just going through all the different calculators which are available under these buttons, and then finally show you the possibilities of the menu. So if I click here on File, Calculator List, you can see that we have about 88 calculators in total available in the program to perform various calculations. So if we click on Antennas, I put this submenu here. Power density to field. If you know the power density in watt per square meters, you can calculate the field. So if we change this number, the field changes. If you change the electrical field, the watt per square meter, the power density is changing. What's the formula? You can see it here. Power density is E squared divided by 120 times pi. That's the formula. But just entering the data in these fields gives you the immediate answer. Near field, far field. What is the relationship between near field and far field regions? Enter the frequency, enter the distance, and get your information right here from the program. Free space transmission. What is the free space transmission? There's two antennas, nothing in between. You have an input power here, transmit PTX, transmit power, and you have here PRX, received power, gain of this antenna, gain TX, and gain RX. Enter all the data here. Now, let's say if we just change it here, and what you see that with 10 dBm transmit power, 12 dBm gain, antenna gain, RX received gain, RX received gain 10 dBi, range 100 meters at 100 megahertz. You will receive minus 20.44 dBm, and the path loss is 30.44 dB. Right. And if you want to convert antenna gain at a particular frequency with an input power and a gain to a E field at, for example, 3, 5, and 10 meters, which are very popular EMC test distances, well, you just change the gain of the antenna. You change the power here, for example, to 200 watts, and it gives you the field strength in volts per meters at that particular distance with this particular gain. If you change the frequency here, what will happen that we have a number here for the antenna factor and the effective antenna area. So these are all the calculators under this section of antennas. This is an imaginary number or complex number calculator. There's two numbers A and B, A real, A imaginary, B real, B imaginary, and these are the results. Result real and result imaginary. So if we perform an operation R is A plus B, you click on it, and the results are given here in the R line. This is the multiplication between the two. This is A minus B, and this is A divided by B. RF mixer. If you are using RF mixers, it's always important to know where is your spurious. So, giving you a quick introduction, let's show you an RF range of 1000 to 2000 megahertz with a local oscillator running from 2500 to 3500. And let's show the IF range, and that is the scale on the bottom of the graph here to 10 gigahertz. And let's assume that the IF is at 3500 with a bandwidth of 250 megahertz. So what you see here, this green block here is the IF, the intermediate frequency of the system at 3500 megahertz. You can see it here with a bandwidth of 250 megahertz, and the upper sideband product, if you mix 1000 and 2500 megahertz, so the addition gives you a signal which is falling into the intermediate frequency. The the lowest B signal is over here and is falling outside the passband. Harmonics are shown here as well, the second and third harmonic here of the local oscillator. So if we move the RF signal, or if we move the intermediate, the local oscillator, you can see here what's happening. Now, of course, there's always harmonics. So let's increase here the harmonics from 1 to 3 for the RF, and to the 7th of the local oscillator. You can see there is a much more number of products here in the RF frequency range. Now you see here the effects, and that some of the signals, if you change the RF, are moving in an opposite direction. And these are these spurs that you have falling into your IF, which are a problem for receiving systems. It's also possible to select the local oscillator isolation. So if you improve the LO isolation, what you can see is that the harmonics of the local oscillator are changing as well. Of course, not always easy to read the numbers here. Click on list. And here you see a list of all the harmonics. Frequency, is it a USB, is it an LSB? What is the relationship of the signal with respect to RF and LO? For example, this one here is minus 3 RF, 4 times LO generated on that frequency with a level of minus 150 dBm, so it's very low. So another effect is if you increase the local oscillator power here, for example, if we go here to a 30 dBm mixer, what is immediately obvious is that the mixing process becomes much more cleaner. So let's say if we go back to 0, for example, you see much more harmonics are generated if you have a low power mixer. Okay, everything is based on the information in this app note from Watkins Johnson, Bert Henderson, from a couple of years ago. Interesting article, and all the information here in this article is translated in this mixer spurs calculation. If you need a little bit more background information, we have a quick link to Wikipedia, and read here everything you want to know about mixers. By the way, this is using the own Windows RF calculator web browser, so it's an own window, and we're not using Firefox or any other program. Good. Digital signal processing. If you would like to calculate filters in DSP applications, this filter design tool allows you to calculate low-pass filters, band-pass filters. It becomes a little bit better if you increase the number of points, high-pass filters, and band reject filters. What's possible with this tool is that you define the frequencies of the filter. So let's say the low-pass filter starts at 0, and this is the cutoff frequency. The number of points that you're using, or the number of taps in your filter. You can change the number of taps by sliding this tool here. And here you see that the filter taps listed in this box over here. Graphically, You see them here. So this list of taps is graphically represented in this box here with the graph filter coefficients. You can of course change the sample frequency as well. So let's say if we go down to this frequency here, and if we make this, for example, 3 kilohertz, then you see here a 3 kilohertz low pass filter. Specification of the filtering, for example, 90 dB. So this gives you a 90 dB filter running at this sample rate with a cutoff frequency of 3 kilohertz. Now you can of course set all these parameters, and the more taps you take, the better is the filter quality. And here you see the impulse response of the filter. You can save the design. It's already given a name. You can save the taps. This is the taps. Of course, if you close this and if you restart the program, you can open a design. For example, we take this high pass filter at 9.6 kilohertz, and there you see the filter with all the settings that were embedded into this saved file. Right, okay. With this more or less demonstrator, you can see what is the relationship between time and frequency. At the moment here we have an infinite short pulse, a Dirac pulse, which is here at the position of t is 0. I can move it. Let's unzoom here, and you see now the pulse moved to the first position here. It is just a little bit wider now. Now what you see, if we make the pulse wider, you can see what is the effect on the real and imaginary spectrum. And it's very interesting to see that if you go back here, make it a pulse width of 1 and shift this single pulse in time, the spectrum behaves as a sine wave. Well, let's go back to 256 samples, the real spectrum and the imaginary spectrum. Now if you just think about this the other way around, if this would be a frequency, or if this would be a carrier and this would be frequency domain, this would be a time domain signal, the I and the Q. So this shows also the fact that there is of course a relationship between time and frequency. And if you do that conversion from time to frequency, the theorem of Parseval shows you that the energy on both sides should be the same. What you see here is all the time domain components, real and imaginary. And if you add them all up, the check in Parseval should be that they give you the same numbers here equal to 1. So if we increase the pulse width to 2, then the recalculated Parseval, so this is according to this formula, the real components and the imaginary components gives you added all up number of 2, and the time domain is 2 as well. So whether you are in frequency domain or are in time domain, the energy stays the same. DSP, this is also a demonstrator. Interesting to see if you want to play a little bit around with modulation. Here, what you see here is a signal generator. So let's take the sine wave generator running at 1024 kilohertz. And if we start this generator, what you can see here is the audio tone. We can zoom in here. And there we go. Audio to graph. And here what you see is that we have two sine waves, 90 degrees shifted. And this is the result what's happening here. We generate a signal. It goes through this route here. It's not going through the bandpass filter. Gives you the real and imaginary output created by this Hilbert transformer. If we use a filter, and now the filter is switched on, you see the effect of the filter on the signal. So there is already some filtering going on. If we increase this filter to 2000 Hertz to 5000 Hertz, let's switch on the filter, the audio is gone. The filter shape you see here, and this is a RF modulator block. So now it's interesting to see if we click here on AM, we have a carrier of 20 kilohertz. It's AM modulated, and here you can see that this is causing an AM modulated signal. I can zoom in here, just select it. And if we change this frequency, for example, to 2048, you see that the modulation frequencies are changing like this. Going to SSB, now the carrier is moving and you can select the upper and lower sideband. So the complete process of digital modulation is shown here. For example, this is FM or phase modulation, and if I increase the modulation on the carrier of the FM, what you see here is the bustle components because of the frequency modulation on the signal. So this is just to play around. You can select different sources. You have a sine wave, pink noise, white noise. Well, there's different types of signals available to play around with. You can play with a bandpass filter. It just gives you a good idea how modulation is working. Again, a Wikipedia page is available showing you more information on the topic, digital signal processing. And if you want to give us feedback, and this is for more parts of the program, then just click on the feedback button and the website, the contact page of the website pops up. Enter your information here and your message, click on agree and send us the feedback. So this is the way to communicate with us and give that information. All right, converters. So if you want to convert units, we have a number of unit converters here. Watt, dBms, dB watts, microvolts, millivolts, dB microvolts, dB millivolts. And how does this work? If you enter here 1000 milliwatts, you see that there is an immediate recalculation to the other format. As soon as you click the box, the green box is the leading box, where the information is taken and recalculated to all the other units here. If you want to convert power to voltage, an important factor is the impedance base. So well, if you want to do this in 75 ohm, just change the base impedance here. This 1 watt is recalculated to these voltage levels and these dB voltage levels. Right. This was also available under the antenna section, and this is a unit conversion for far field. So if we have a field strength of 10 volts per meter, this is the dB microvolt per meter level. Ampere per meter, based on 377 ohms in free space. Now you see magnetic field strength, power density, and magnetic field. If you know the watt per square meter, the power density level, type in the power density level and all other numbers here are calculated from this green box. Fine, let's go to the next one. Attenuators. We have two calculators to work with attenuation. This one gives you the opportunity to start with an impedance, for example here of 50 ohms, and We can take here, for example, a 100 ohm impedance, or let's say 1000 ohm. Sorry, let's go back to 100. So with the calculated attenuator here, we can generate, or let's say calculate, a matching attenuator to match a 50 ohm to a 100 ohm system. What is required? A minimum attenuation of 7.66 dB. In this case we have 10. If you go below that minimum required, you get a warning. If it is higher, then there is no issue. And based on the power level at the input here, you can see that this power level, 30 dBm at 50 ohms, gives you the RMS voltage of 7 and the peak-to-peak voltage of 20. The same voltage calculations here. And if you have a attenuation of 10 dB, and if you apply 30 dBm, which is 1 watt, what is going to happen then? That your output power is 20 dBm, which is 100 milliwatts. So 1 watt minus 100 milliwatts gives you a total dissipation in the attenuator of 900 milliwatts. So this is the exact outcome of this attenuation, and each resistor is indicated here, resistor value and resistor dissipation. So you can select the correct resistor for the application. Now, if you have a bad VSWR, also attenuation can be used to have the generator see a better load than the load actually is. So let's say if, for example, if the load VSWR is 10, in that case, the return loss is 1.75 dB, so that's not too good. But if you add here a 5 dB attenuation, then the 1.74 dB return loss is going to be improved. You see here VSWR is 10 and the load sees 1.7, and the higher the attenuation, so for example let's go to 10, so load VSWR 10, attenuation is 10, now the VSWR seen by the generator is 1.18, and the reflection loss is improved to 21.74 dB. If we just bring this one down, you can see that if the attenuation is 0, the return loss, 1.74 dB, is the same here as the improved return loss, because there is 0 dB attenuation and there is no improvement. VSWRs as well are the same. All right, so we go to the next one. Basic electrical calculators. This one you can use if you have an inductive load and need to find out compensation. So we have a voltage here, we have a power line frequency here. This is an inductive resistive load, and here you can see the real and imaginary components. Now if you want to do the compensation, you click here on the compensation. You see the current flowing through that capacitor here. So if we increase that capacitor value, well, you can see what is the reactive value and what is the cosine phi. So that is actually what you want to reach with this. Parallel resistors, or series C. So if you have, for example, these resistors in parallel, so let's wait a second. Let's go back here. Let's just take some numbers. And we take one here as well. If you calculate, this is going to be the equivalent resistance of all these values here in parallel. If you do a change and say, okay, well, I want to calculate Capacitors, of course, series capacitors is the same type of calculation as series resistors. Right, electromagnetic compatibility. Here we have some interesting calculators for EMC, which are the following calculators. This is an RF immunity test configurator. So this is to see roughly how a radiated immunity test setup can look like. Now I have some examples here on the system. So let's say if we take this one, what you see here is the performance of the amplifier. The blue line is the 1 dB compression power of the amplifier, and here you see the field of this amplifier. At a distance of 3 meters, we have 20 frequency points in total, and we have a field uniformity in the chamber of 3 dB. Now with this table here, you can see the cable loss, the type of antenna gain, the antenna gain value, and the total field which is generated. Now with this calculator you can design a system, roughly design a system based on amplifier power, antenna gain, and cable losses. A more detailed movie video with instructions will be available later under in this configurator itself. Here we have a YouTube link in the future. Specific absorption ratio, or the exposure calculator. This has to do with safety, and what's interesting to know is the watt per kilogram and the incident power density, 0.27 watt per meter squared. We have an E field of 10 volts per meter. This is the conductivity of the tissue. This is the mass density. And based on this information here, you get these results. If you have transmit power of 40 watts, look here what we can do. If we know transmit power, antenna gain, and distance, for example, if we decrease this distance to 10 meters, you can see here that volt per meter level is increasing. And if we change this to, for example, 100 watts, 50 dBm, then the volt per meter level goes up. The shorter the distance, the higher the numbers here on the exposure. So this is a calculator giving you the opportunity to give base numbers like field, conductivity, mass density, gives you the output here. If you change the parameters here, we calculate the volt per meter level from these numbers and enter them in the box here, providing that information as well. So a flexible tool to do this type of investigations. RF conducted immunity, or BCI, bulk current injection. With this calculator, you're able to create a system. Let's say we take 5 frequency points and we take an injection probe, for example, model F140. The length of the cable between the amplifier and the probe is 10 meters. What is the loss at 0.1 megahertz? Let's say it's 1. At 1000 megahertz, it's 2. Now, and the data for the probe is predefined in a table in the software. And what you can see here is that as a function of frequency, the cable loss is calculated, and this is the injection loss of the probe. So the required 1 dB compression power, so this is this curve, is required to inject 100 milliamps with a modulation percentage of 80%. You see here the peak current, start frequency, stop frequency, and the line impedance. If we decrease this value here to 50 milliamps, then in that case, we select the probe again. Take this defined definitions again, and these here is the performance requirements, and this is the current that you want to inject. Right. AM modulation. What is the effect of modulation on the number of dBs increase of a signal? So if you have a carrier, there is 0% modulation index, and the PEP value, so that's the peak envelope power, the peaks on the top of the sine wave is 0 dB. So let's give 31, 37% modulation index. These peaks here are 2.7 dB, 73 dB higher than the normal carrier wave. So let's go to 80%, a popular number. In that case, what you see, 5.11 dB is this peak with respect to the level of the unmodulated carrier. TEM cell, popular for EMC people, popular solution for calibrating field probes. How does this work? RF generator, RF amplifier. The amplifier produces an RF signal on the septum, which is a line here in the cell, and here characteristically terminated by 50 ohms. If you apply 10 watts of power into 50 ohms in this cell, where the D, the septum height, is 100 centimeters, the field strength here above the septum and below the septum is 22.36 volt per meter. Lowering the power lowers the field. Making the cell smaller, for example, to 50, so from 100 to 50, you see it doubles the field. So a smaller cell has a higher field intensity. So with this calculator, you can find out how many power is required to generate a field in a particular TEM cell. Same applies to a strip line. In this case, we have a strip line, which is a 100 ohm strip line. You can see it here. Oh, sorry, it's a 75, but make it a 100 ohm strip line. And we drive that strip line with a signal generator, an RF amplifier, which is a 50 ohm output amplifier. And here we see a 100 ohm strip line to generate the field. So to do the matching, an RF attenuator is inserted here. Minimum attenuation for the attenuator to match 50 to 100 ohms is 7.7 dB. So let's say if we put here 8, then we are as close as possible to the minimum requirement. And then it's obvious that if you create 1 watt of power with this amplifier, with a septum height, a strip line height of 40 centimeters, you are generating almost 10 volt per meter here between the septum, between the strip line and the ground plane here. And these are the RMS and peak voltages of the strip line. Good, so this was our section EMC. And then there's quite an interesting package of filter calculators. We have Butterworth. We have Chebushev. Let's put them here. I won't show them all. This is an interdigital filter. Narrowband filters for communication applications. Add the number of elements, the required ripple, center frequency, and it gives you here the mechanical design of such a filter based on your RF requirements. And if you need to do some matching, lossless matching of a generator with a impedance lower than the load, so the generator load is lower than the load of this one here, you can use this matching network. So do the calculation. So in this case, XL, XC are calculated here The bandwidth of that solution is 38 megahertz, and the corresponding L and C values are given here. Now this is for 4 configurations. Source is lower than load, source is higher than load, source is lower than load, source is higher than load. And what you see here, this is a low pass network and this is a high pass network. So flexible calculator as well for 4 scenarios of LC matching between different loads. So let's select here a Chebushev LowPass filter. What you see here is the different elements of a pi topology and a T topology. Select the order of the filter. You want 0.5 dB of ripple, 10 MHz cutoff. If you calculate the elements here, you see the values. So that's a parallel capacitor, series inductor, parallel capacitor, series inductor, parallel capacitor. So this is the T version and this is the pi version. Same is applicable for the Butterworth. Let's take a 9th order here at 1 megahertz. Calculate, and of course you can also change the base impedance so that filters on different impedance levels with different orders between 1 and 9 for various frequencies can be calculated. I won't discuss them all. It just gives you a good idea what is possible with the program. Radar, for people working with radar. Let's look at this one first. If you're doing radar target simulation, you can find out and see what kind of levels are expected or can be expected if you do testing of a radar system. How does this work? Here is your radar target generator position. And what is a radar target generator? A radar target generator receives the pulse from the radar with an antenna of a certain gain, processes the signal, and returns it as a signal back to the radar. So you are doing a simulation of a target. So you can test the radar without having the target available. The target can be a missile, target can be a ship, the target can be an airplane. So with a 16 dBi antenna, and this radar antenna operating at present on X-band 9500 MHz with this power level 100 kilowatts, a simulated RCS of 0.1 meter square, which is minus 10 dB meter square, you can see here that on the radar target position we have these values. The radar target simulator is positioned at a distance of 800 meters from the radar, and that target simulator is receiving 156 watt per meter square. The E field is 240 volts per meter. Now all these details here you can see what is happening at that radar target simulator. With that energy received, using this antenna to return the signal after processing, you can find out here what this radar is receiving. Now you can move the simulator on a position with this slider, but you can also move the target, the simulated target here, to a larger distance. Now at this distance for the target, which is 162 kilometers, and the tower position here at, let's say, 985 meters, this target generator requires 64 dBm minus into a 16 dBi antenna to generate minus 119 dBm on the radar receive section. So with this simulator, with this simulator calculator, you can find out, okay, what is the position of this generator, what is the position of the target, and just analyze all the data. Change frequency here, change power level here, change the RCS here, tower position, and target position. So very flexible and gives you an immediate result, how many dBm is required into this antenna to create this particular power level at the RX antenna output. Of course, if you increase the gain, you see that the TX power level of the radar target generator is reduced. With a better antenna gain, you need less power. Good. These are some various functions of radar calculations: antenna aperture, pulse repetition frequency, maximum radar range, and target gain factor. Won't discuss them more. And this is a Doppler calculator. So you have a flying object. It's illuminated by the radar, and it gives you the output of the Doppler frequency. General RF. Oh, there's a bunch of calculators here. This is an interesting one. Cascaded amplifiers. From 2 to a total of 6. In all these boxes, you define the individual performances of all these individual amplifiers. So let's go back to 2 only. And if this stage 1 here is a noisy amplifier, so let's increase the noise factor. And if this is, let's say, the pre-amplifier, this is the LNA, you can see here that this 12.5 dB noise factor with a gain of this stage of 20 dB with a lower noise factor of 2 dB, it's 10 dB gain, 2 dB noise factor. If you reduce this noise factor of this LNA, you can see that the overall noise is reduced. Further outputs are, we define the gain, the noise factor, the individual 1 dB compression points, and the IP3 distances. Now this is calculated for the entire chain, so if you have all these parameters filled in, it gives you the total result of the chain here. Intercept point. Well, if you have two carriers of 50 dBm, and if your intermodulation products are 20 dBm, your third order IP is 65 dBm, or this power level. So if you decrease them, or you make less spurious, you see that the third order IP is increasing. If you make a bad amplifier, 50 dBm with 40 dBm intermodulation, you can see that the third order IP is 300 watts only. So this is how you can check this. There's a second one that gives you another calculation. You define the power levels of the carriers. You define power level of this one. You define the power level of OIP3, output intercept power 3. And if you change this, you can see here what is the effect on the two spurious IM2 and IM2. So in this case, with these F1, F2 levels, so frequency 2 is a little bit less in power than the other one, you can see here that IM2 is lower than IM1. Passive intermodulation. Now, this is a passive intermodulation analyzer. In this case, in startup defined at some telecom bands. So if we do a single sweep, what we see here is that the green signals are the RF carriers. So if we just switch these off and keep the highest and the lowest one enabled, if I take a sweep, then you see carrier 1 and carrier 2. The red lines here, if you zoom in on them, they are masks. So here you see the mask of the channels, of the receive channels. These are the TX channels, and this is the RX channel. So this is for a full duplex system. where positive intermodulation is always going to be a problem. Now, if you switch on this nonlinear transfer function, let's add more carriers here. What you can see, if we change these parameters here, you can see here that intermodulation products are generated. Now, what's interesting is to find out is, okay, where are all these carriers with respect to the masks of the received channels? Is my receiver jammed by a intermod product from all the signals that we have in the air on the transmit side? You see, if I switch on these carriers here and I sweep, that there is intermodulation products into this channel, something you do not want. So a nice analyzer, you can change the RX IF bandwidth, you can change the relationship between the two, you can change the frequencies. Very flexible tool. VSWR, mismatch and return loss. So now if you have a VSWR of 3, the coefficient of the reflection is 0.5, reflected power 25%, mismatch loss 1.25 dB, return loss is 6, and the reflected power is 75%. So just change here the VSWR and all the other parameters are immediately recalculated. Frequency to wavelength. I'm now on the kilohertz scale. So if you change this here, 63 kilohertz is this wavelength. Let's go to gigahertz. You see it's a very short wavelength. If I go to megahertz, it gives you 583 megahertz is half a meter. Frequency to wavelength. This is the other way around. Wavelength to frequency. So if we take centimeters, 100, you are at 300 megahertz. If I go to 300 megahertz, which is the FM band you can see here, an FM frequency. So this is conversion between wavelength and frequency. We already have seen this one in another calculator. L and C reactance calculator. Define the frequency in megahertz or kilohertz or gigahertz. You have a capacitor with a value pico, nano, micro and millifarad. Inductor value microhenry, nanohenry, millihenry and henry. From these input parameters, the reactive capacitance and the reactive inductances are calculated. Resonance, well, you define your capacitor with here the multipliers. You define those two, gives you a frequency of so many megahertz, wavelength corresponding. If you want to make a quarter wave stub, for example, for matching or as a balloon, or with using, if you're building a Wilkinson power combiner, with the velocity factor here, you can find out the quarter wavelength stub, the exact mechanical length that is required. KTB, noise figure, noise temperature, and vice versa. And the impedance of a coaxial line. So if you have this as the mechanical parameters, inner diameter, outer diameter, the relative permittivity, a length, and then the corresponding length of the quarter wave stub, calculate here. So from this ratio between inner and outer with a relative permittivity of 1, the epsilon is 1, you get a 24.3 ohm coaxial line impedance. Single layer coils. So if you want to calculate a coil here, change the parameters, it gives you the wire gauge, the best wire gauge. If you have a wire gauge, for example, of 24 and a length of wire of, let's say, 20 centimeters, this is the corresponding inductance in microhenry. So each piece of wire creates inductance, and this is what you get. Good. And then the final one in the RF is AM to PM conversion. So based on third order IP input level and gain, you can find out what is the AM to PM conversion of the system. Number converters. So just enter here your decimal number. Get your binary out, octal and hexadecimal. Transmission lines. Well, there's various configurations. Two parallel lines, a line above a ground plane, a line between two ground planes. This is a parallel situation flat. Here, this is the outer one. This is the transmission line. This is the normal coax, and this is a square coax. Well, change these parameters here on each calculator. The green box becomes red if it becomes outside the accuracy range of the calculation, and you can also change here the relative permittivity or the epsilon. Shielding. Well, this is the plane wave shield calculator. So if you have a material, let's say aluminium, and a material thickness of 2 mil, then the attenuation of the field, you have here the field outside, the field traveling here through the shield itself, and this is the other side of the shield. This is the total attenuation for aluminium. If we go to gold, it performs much better. Waveguides. Waveguides are often used as solutions to transport something into a shielded room. Could be a fiber or something non-conductive. If you have a rectangular waveguide or a circular waveguide, well, change the dimensions here and it gives you the cutoff frequencies. Skin depth. Well, select a material, for example zinc, at a frequency, let's say, of 0.5 megahertz. This is the resistivity and the relative permeability of the material, and the skin depth is 172 micrometer, and this is the corresponding formula. Cavity. If you have a resonating box, define length, width and height, select the modes, and here you can calculate the frequency. Common for all types here is the relative permittivity and the permeability. And there is solutions for rectangular, cylindrical and also PCB planes. Near field shielding. So at a low frequency with a distance of 1.1 meter. Now let's say here you can see the performances of different materials. Now let's say if we want to highlight the performance of zinc, the thicker line is zinc. If we change this to, for example, to silver and scan, you see that silver is doing a much better job. If we change this to aluminium, or sorry, this is stainless steel. Oh, something is wrong here. So this is a bug I have to change. Sorry for that. Good. So this was a quick run through all the different calculators. If you look into the menu, what you can do with the menu in the calculator, This is a list of all available calculators, and this is a nice one. If you have a list of calculators you're often using, you can say, well, I have calculator 1, I want to use this one, and I use this one here. I have also the LCRX, so we define here 3 popular calculators, and I want to position it on this place on the screen. So then I say close, favorites, open, and here you see your favorite box with calculators. So if I click on this one, here's the Butterworth, click on this one, there's the other filter, and click on this one, it gives you this calculator. So it's a shortcut menu. You can just close it by clicking this box. If I say favorites open, it is coming back to that same position. And if I say define, and if this place is a little bit cumbersome for me, I say okay, put it on that position. So if I say file, favorites open, then you now suddenly see it here on the screen. So you can place the favorites bar on any position on the screen. rfcalculator.com, there is a web browser form built into the program, goes right away to the website of rfcalculator.com. There's a help menu here, user info. There is version information. Here you see the various updates. So this is an update screen with all version updates. My ID, your ID number, the type of license, your name, email address, and company name. And check update confirms here in this case that we are running the latest version, and this is checked through the website. So there is on the website, the version number is embedded in one of the pages, and we're checking that. So this is a quick rundown. By the way, the green box here means that you are connected to the internet. And that gives you the information that if you want to go to the website, that at least there is an internet connection available. We didn't discuss this one, PDFs. There's a number of PDF application notes. For example, the Watkins-Johnson application note on the mixers. So this is a quick PDF reader embedded in the program. Something about PIM, passive intermodulation, application note, mixer spurs, DSP modulation, radiated immunity. So this shows you how to configure the program and gives you further instructions. In the future, each individual calculator will have a YouTube link, and instead of a paper manual or paper explanation, there will be a video available showing you how is the calculator working, how do you work with it, how do you set the parameters, and how do you obtain the output. Good. I hope that gives you a good impression of the software. Thank you for your attention.